Let's continue. So far we have defined several elements. We have defined the output images for the safety and the regular, and the input images for the safety and the regular, and we have also defined the plans for the safety and the regular, and we have defined the events for the safety and for the regular. Okay, what's needed is to define the requirements for the safety and for the regular. Okay, we were able to define what's so-called RS prime. These are the direct or these are the safety requirements that are derived directly from the sensors. However, for some reason that will be clear later, this is not all the requirements needed for the safety. In other words, RR prime and RS prime are not RS and are not RR. In fact, as he have mentioned here, and we know why RS prime is just a subset from RS. So first of all, let us focus on the regular requirements. Okay, we have divided the events into safety events and regular events. Safety events are events that are monitored for safety. However, these events occur during the normal operation. Okay, so these events can be evoked or they can be monitored also by the regular supervisor. Okay, that's why he is mentioning here the regular requirements can be formulated for events in sigma S and sigma R. So RR prime, what's RR prime? RR prime, these are the regular requirements that are provided by the user. Okay, these are not related to safety. However, we need to split them to see which of them will be included in the safety supervisor and which of them will be included in the regular supervisor. So first of all, we split RR prime into two sets. One of them will be RRS. RRS are the set of the requirements that are defined based on the events in sigma S. And RRR are the set of the requirements that are defined in terms of the events in the regular sets. This should be clear enough. Okay, so what's next? We will further work on RRS. Further work on RRS. And by the way, the set of regular requirements will be simply RRR. This is I'm just mentioning this result just to keep you focused. Okay, the problem is with RRS. Okay, we can just plug all RRS inside the safety supervisor. We can do that. However, if we do that, we will be sometimes we will be violating requirement 4. Requirement 4 requires that the requirements in the safety supervisor will be minimum. Okay, so that's he's saying as requirements in RRS should be included in the regular program whenever possible. You cannot just plug all of them into the safety because you will just increase the size of the safety supervisor. So if any requirement here can be included in the regular program, you should include it. Okay, so how to identify these? The regular, we will loop for each requirement in RRS and see if this requirement has a variable that is subject to change and it is included inside the safety image, then we will take this one and put it in what's so-called RRSS. And we will also loop again and see for all the requirements inside RRS if there is some location that is intersecting with the locations in the plans of the safety supervisor and this is subject to change, then we will also take this requirement and put in RRSS. Okay, so what now? So we will return back to RRS and disjoin it into two parts. Okay, we will define what's called RSR and we will deal later with this RSR, but simply RSS will be a part of the safety supervisor. Okay, the safety supervisor requirements now includes RS prime and RRSS. Okay, let us have a look down here just for you. Okay, this is what we have mentioned, RS prime and RRSS. We are just left with this RD. What is this RD? So he is mentioning that for each event in RSR that can be evaluated in the regular part, then the evaluation can be communicated to the safety part. Okay, why we need to communicate to the safety part? Because this regulation is based on an event epsilon s, sigma s, okay, an event inside the plant of the safety supervisor. So we need to communicate that back from the data buffer. You can refer back to figure 3 to see what this data buffer was needed or was used to communicate between both supervisors. So we'll communicate what we just mentioned from CR to CS by the DR. Okay, that's what's mentioned here. So we will communicate what the information in RRSR because it is related to the safety events. We communicate to the safety supervisor. So how to communicate this? We will focus on each event sigma that exists inside sigma s that is being used inside RSR, okay, and we will not communicate. We will communicate the exactly one condition evaluation instead of communicating each sigma c. No, we will collect them all in only one c sigma. C sigma is the collection of all conditions that are invoked for sigma, so that we can make the communication only once and satisfy requirements R4 and R5, which simply state that the safety supervisor should be as simple as possible. Once we have this C sigma, we will be able to define what's called V sigma. V sigma is simply the result of C sigma. Okay, so we will define what's so-called RD. RD is a simplified version of RRSR. It's equal to the set of requirements that are defined on the event sigma that belong to sigma s, where V sigma is defined by equation 16. Simply or with difficulty, this is the requirements for the safety supervisor. RS prime already mentioned, this was directly. RRSS, this was extracted from the regular requirements. And finally, RD, this was a simplified set of requirements that we have been extracted from the regular requirements. And RRR was already described a few minutes ago. So now we have the requirements for the safety and for the regular ones. In order to access variables from other program parts that are saved in the memory of the regular or the memory of the safety, some evaluation results have to be communicated through the, as we have already mentioned, through the buffers, data buffers. So from equation 3, the conditions of the requirements in RS prime cannot contain location references. You can just refer again to equation 3. It's telling you here that the safety requirements cannot contain any location. That's what's mentioned. And the reason for that is that these safety requirements must be obtained directly from the sensors, not from the states. So from equation 3, the conditions in RS prime cannot contain location. And I advise you again to revise equations 14 and 16 for C sigma that cannot contain location references in PS, okay, to components in PS, because C sigma was defined for components only on P. So these are the DR and this is the DS. As you can see, this is the buffer of the regular, okay. It contains the set of all requirements based on V sigma. V sigma was defined above. that belong to RD, union again what's called by VL. These are all the requirements in RRSS, where there exists some sigma that belongs to the location C, intersection with the locations in P, and for DS we have something similar. This is VL. These need to be communicated from the safety requirements from the safety supervisor to the regular supervisor, where this VL is needed to satisfy the requirements or to check the requirements for the regular part. And we define these variables such that there exists some L that belongs to a location C, the location C from the regular requirement, and it's also located in a plant that is belonging to the safety requirement. I advise you to read this equation twice and try to understand what's being described. For the proof, I'm just going to skip the proof. It much mathematical details. Finally, and I'll also skip the safety implementation because it is related to PLC, the function block diagrams, it's related to the PLC technology, so I will just skip that. So finally, I will go to the method illustration. For the illustration, he is referring to a rotating bridge, and for those interested for a more elaborate example, he is providing a link, and this link, by the way, is active on GitHub, and this is the result. You could see this is the result of the link. This is a PDF, and this PDF is explaining the location of some bridge in Netherlands. I advise you to read this and try to understand more what's being presented. For the simple example here, this is only one bridge, only one rotating bridge, with the following components: a boom barrier, a bridge deck, a vessel traffic light, and the emergency stop, and 3 commands: open the bridge, stop the bridge, or close the bridge. Now, to control the position, there is an actuator, and the model of actuator is shown here. It can be either ordered to open, or can be ordered to stop, or to have an emergency stop, or to close. And also once it is closing, we can just give it the order to stop or to have an emergency stop. This is the component. Now, what are the requirements? The requirements are based on these sensors. The sensors are either telling you that the boom barrier is closed, or vessel traffic light is red, or we are having an emergency stop, or when having an open command, or when having a close command, or a stop command. These are the Boolean input variables. These are the sensor readings, and this is the image. The image here includes all the sensor readings, as we have already mentioned, and the actuator signals are the output images. We are either instructing the actuator to open or to close. And these are the hardware mappings. The hardware mapping means that the event open assigns a true value for the output image Q open, and the event close assigns a true value to the image Q close, and the same for the other ones. Now, these are the requirements. The requirements below are either safety or regular requirements. For instance, this one, which is a safety requirement, it says that to issue the event open, we need to have a true value for IBBC. IBBC is the boom barrier closed. You cannot issue open unless the boom barrier is closed. Again, this is needed to make sure that the mechanical part and the electrical part are not damaged, so it's a safety. To issue the command open, you need not IES. So what's IES? IES was the third one here. It's emergency stop. So to try to open, you need to make sure that you did not issue an emergency stop command. So these are the safety. I advise you to read them. Okay, let us have a look at this regular requirement. To issue an open, you need IOC. So what's IOC? 1, 2, 3, 4. This is the fourth one. 1, 2, 3, 4. Open command. To issue an open command, or to issue an open, you need to have the open command. It's like simple like that. Okay. So in other words, the user has to press the button of the open command in order to be able to issue the open command, and it's clearly a regular requirement. Okay. And again, ICC not. So what's ICC? This is the one before the end one. This is close command. Okay, to issue an open, the close command should not be pressed. Okay. For the supervisory splitting, and now it seems that all the requirements are clear. For the supervisory splitting, it's clear that first of all we start with IS. So he will take all the sensor signals that are present in the safety requirements, IBCC and IES and IVTLR. These are the three of them, and the rest will be in the regular requirement section or the regular requirement image. And for the output image, you can verify that when we go through equation 6 and 7, the output image for the safety will be Q open and Q close, and QR will be a 0. And the same, you can verify that we'll have the plan for the bridge only for the safety and no plans for the regular requirements. You can also see that this is the resulting for epsilon S and epsilon R. I believe you can go and check the next steps. Okay. Again, the main problem, the main issue with this paper is that the requirements were not described using automata. So in order to have something useful with SuperMecha, I advise you to try to describe the requirements using automata and try to sketch or to develop the supervisor, either it is a safety supervisor or a regular supervisor, using the methodology that have been described in the past videos. Thank you very much for listening. I hope that you have learned something useful and new. Thank you very much again.